in general, what I have showed you, it mostly so far has been something I'd call constant support. So what we've had is some sort of structure that had a motor on it, and then there'd be inside the structure there would have been some rails, some sort of bearing or bushing in here, and then the actual carriage. That's what this right here is, the carriage, and this right here is would be called the block, the bearing block, and this would generally be called a rail. Just kind of general terms here. But the key to this is that when this carriage, and so let me, we'll just draw that, we've got some, load that we're carrying on this thing. The key to this is that even though there might be pitch moments and yaw and roll and those, the moments that happen during acceleration, the bearings, the actual little balls in here, pretty much have a constant support throughout the length of travel or length of motion of this whole thing. So whether this block is there, whether it was over here, it's got the same support underneath it. The thing about constant support to keep in mind is if this load that you have is, over here, this part of the stage is what we call intrusive, meaning the load may have moved back to this spot, but it left a whole bunch of the mechanics out in the motion area. It didn't move. So the good thing is it's constant support. The loading is always the same, but this part here is always out in the load. Now you could have done something like this. You could have, and sometimes we do this, you would say, okay, let's make this something like this, and we're going to actually mount this to the table. And when we put the motor on here, then this moves back and forth, and in a way you make it so that you still have constant support, sort of, but now if you're actually putting this mass, the trouble with it seems like you still have the same thing, but you don't, because if you put this mass, that we'll just draw the same kind of mass that if you mount it to the carriage, and it seems like it has constant support, but it doesn't, because these little balls that are in here, the little ball bearings, are now, sometimes it sees a moment load that way, sometimes it sees direct force, and sometimes it sees a moment load that way, depending on where it is in the travel. So what you get out of that, nothing's necessarily bad or good about any of this stuff. It's just the main thing that you constantly have to look at and deal with is deflection. Deflection under load. And if you're trying to keep, if your goal is to keep a point, let's say that the key spot is right here on this load. That's the key spot that you want to move in 3D space. Keep in mind, what you get to move, or actually what you get to do, is program some motion, some electromagnetics, and then the motor turns a nut which interacts through some squishy bearings, some little, let's just call them little teeny yoga balls. Although they are steel, but they're little steel springs. And then you have the case where, did you get this to be, is it perpendicular? Do you have a 90-degree mount here? And so what happens, this point that you're trying to keep move in space has all sorts of motions that aren't necessarily ones that you programmed. And that's including the mounting surface here. If the mounting surface isn't perfect that you mount your stage onto, And you've got these mounting holes here, and you're going to mount it to something. But if the something isn't flat and the something wins, then now all of a sudden this point in space is going to be moving forward and backwards more than it should with the motion just from the block, because it's doing this number, right? As it's going along. And in fact, most manufacturers, when they make a measurement of the straight line accuracy of a stage, they do pick a point. Usually it's a point somewhere about 2 inches off, is a pretty, or 50 centimeters. Yeah, 50 centimeters off of the carriage of, and that's the point where they actually tell you how much did this point go forward and back throughout its travel. All that's before you even deal with deflection. Now you add in a situation where you get a non-constant support where this bearing right here is underweight. When it's out over where I put it here, this bearing here is really squished, and this one over here may not have any force, any pressure on it at all anymore, because this very end of the bearing, these last 2 or 3 are seeing all the load based on how you added the load to it. So, and that changes when this comes back over here. All of a sudden this side is the squishy side, and the left side there is not under load. So constant support has some good things about it, but it is intrusive. Okay. Some other examples. So the opposite of constant support, obviously, is guess what? Non-constant. I mean, pretty great words we use for this. So constant support, flip it over, you have non-constant support, and you're dealing with the bearings differently. Another one. Here's another one. No, let me show that one later. Most linear guides that you'll come across, like this, they're constant support because they travel back and forth along a rail. You can see that, I presume. But there's one other thing that is another category that we've got to deal with, which is recirculating. Or the opposite of recirculating is non-recirculating. So what I mean by that is, so on these little bearings where we're using all these little balls, I showed last time where they actually were, as they went along, they would go into the loading zone, and then they would come out of the loading zone, and they would travel at kind of double speed backwards, and then get back ready to go into the loading zone and kind of pop in there. And that's where some of the noise comes from. And this non-recirculating essentially gives you the ability to take this rail and make it as long as you want. You could have 10 feet or more of rail, and this bearing block would just move along the rail. Now, at some point, you have to actually join rails, and there's practical limits to how long you can make the rail. But generally, your 3 meters is a pretty standard length. We used to actually have a machine that when customers would want a certain length of rail, and we had a relationship with THK where we could get the THK parts at a discount, and then we put them into machines, and we actually bought a special machine that would cut these rails. And it was a special wet cutting machine because they're really hard. This is a bearing surface that's in here. And so you can't just cut them with a standard cutoff saw. It was a special wet cutoff saw, and that customers have to buy the whole rail. And then if they didn't need the whole rail, they still would, we had cut off stuff. Let's see. So recirculating. Recirculating is mostly linear guides. Let me just Okay. Non-recirculating, I'm going to switch to the next page here. So non-recirculating bearings, one of the kinds is a ball slide. This is called. I'm going to draw the end view of the bearing structure in this. If we have the overall carriage, so if we have this overall carriage, then inside of that, you have another, the part that you would actually attach. So this is moving. And this is got the bolts. This is, securing down. This is secure. This is non-moving. And what they do in here, what the bearing structure looks like is they'll put a rail here and a rail here. Oops, I drew this bad. Hold on, I gotta erase something here. I gotta erase this. Okay, I gotta redraw that. I gotta redraw it up here a little bit better. Okay, there we go. Now I'm happy. Okay, another screw. Okay, so you put a couple of rails. These are just thin stainless steel rods. There's two there, two there, two here, and two here. And these rods go, the length. And then in between there is the ball bearing. In this case, it's a pretty big ball bearing. This is a little piece of, I don't know, it's not fiberglass, it's not Delrin, it's some sort of bearing retainer. And it looks like this. It's a piece of phenolic or something that has a bunch of holes in it. And the bearing, the little balls, there's one ball per hole. And that goes, if you can kind of see here, you can almost see, let's see if I get this right. There you go. There you can see the actual ball bearings. There's one right there, one right there, one right there, one right there, one right there. You can actually see the little ball bearings. And here is, if I show this closely, you can see there's the rails. The rail there's a teeny little rail right there. It's probably 1 millimeter in diameter. And then there's one right there, and that's 1 millimeter in diameter. So, and then there's two more in this part here. And so this moves back and forth. And if you can, I do it with my pinky here, but you can see this thing is just, it's super silky smooth. There's almost zero friction in this thing. And the reason is because if you think about the kind of contact in a ball slide, what kind do you have? Do you have line contact, point contact? You have kind of the worst thing that we talked about, which is right here. You have 4 points of point contact. So the ball bearing is captured between these 4 rails, and then the bearing retainer makes them move back and forth through its non-constant support travel. So typically these one of the things that happens when you have this long bearing area, and you can see this bearing area in here is 2.25 inches long is the bearing area. It's actually quite long, and the travel with this, if we look, we start here, the travel there is only about 2 inches of travel. So we have this monster device, and it's only about 2 inches of travel. There's a little bit there, and it hits, and what stops the travel, if you look really carefully, is the bearing retainer actually hit the end, right? Bang. This is nothing more than a drawer slide, except for on the drawer slide, you would never find these. These are preload screws. So that as they set this up, these preload screws will be pushing on a little thing. So this preload screw pushes against those and essentially cinches the whole thing up together and gets rid of the backlash or the slop in the bearing. So it's tricky to set these up. You set them up again so that it slides really easily back and forth. It's very low friction, but you don't want slop in it. This is about a $100 bearing probably, this little 2-inch bearing. And the places that somebody would use this is when they want very straight travel. Or very straight line accuracy. It would be probably the proper term, where you want straight line accuracy. So if you put a laser on here and pointed it to, you know, out here towards the wall, throughout this travel of this thing going back and forth, that laser dot on the wall probably wouldn't even move. It's very accurate. These are made out of aluminum for the most part. So ball slide, they do have their uses, and the key is very straight and very low friction. Do you remember why we want very low friction? Anybody remember why we want low friction?
So that it's not hard to overcome the initial friction when you want it to move a really small distance.
The key is the last thing is what you said. Yes, when you want to move a really small distance. You know, I did a machine down in the Bay Area one time, and the travel we were talking about was submicron motion is what they were after. What they needed to move this thing, and when they made a move, for instance, if they put a microstepper on it, in this case, it was not a microstepper, it was a linear motor with an encoder. It was a closed loop system. And the encoder had a mark or a count. I think it was every half micron. Well, if you think about what a micron is a millionth of a meter. And so you start talking about putting, you know, something that's a meter wide, that's only half a meter, obviously, but you know, a meter over here and over here, and then dividing that up into over 1 million spots. That a micron is tiny, 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 and submicron motion is almost only possible when you have the friction that allows you to do it. If you have any stiction at all, and so a lot of times when you know, the only thing better than this ball slide. I'll just write it down here because we don't really talk about it, is air bearings. So at some point you have to get away from, and this is almost like in your physics, you have the frictionless table that you always talk about, so that you can work on problems without having to deal with that. But that's what an air bearing is it allows you to almost have infinite small motions because you have no friction. And the ball slide is a mechanical way to get pretty close to that. Okay, so this is non-recirculating. There's another kind of bearing that is of interest that we have to talk about. There's two more. Let's go next to, so everything we've done up to this point has been, you know, if we summarized all this, everything up here has been ball bearings. And so you had point contact, and then we went to Gothic arch and radius groove, and you started to try and spread that point contact out over a grooved surface that it could run in. And that's kind of the best you can do. So the next thing we'd like to try and do is do line contact. Can you imagine if you built a car, right? You built this car, and then normally you think of having tires with a big flat bottom on them, and some are thicker than others, but can you imagine what would happen if you had a tire that looked like this? You know, and that ran along the pavement. You would have very, very low friction, but you wouldn't be able to hold much load. but it would be really low friction, right? Because there isn't a lot of difference in velocity as it rotates. There's not any scrub that happens. There's not any part of this motion right here that is any different velocity. So the motion is super smooth. One of the things that you could do is you say, well, how about if we do something more like a tire, or a train track where you have a rail, and then you have something that is not just a point, not a ball bearing that comes to a point, but you have some sort of roller mechanism. And so now if you had some sort of roller mechanism that rolled along a surface, right? And let's say you even contained the surface somehow. Let's say you gave it a little ledge here to run in, and over here you gave it a little ledge that it could run within. And yeah, we did something like this. So, you know, we ran it down a channel, some sort of to contain the bearing. All of a sudden what would happen is now the load that you might be able to put on this, let's just, you know, let's attach a load to it somehow up here, some magical, mystical mass, that now that load has line contact along here instead of point contact. And so the load carrying capacity of anything with line contact goes way, way up compared to anything with point contact. Even though we have this little ball bearing, and it has, you know, a whole bunch of little balls that can carry the load in a radius groove, it's not, they're still little teeny balls, and they have a limit. So this roller all of a sudden has line contact, and it doesn't deflect the same underload. But there's a big problem with trying to make a roller work in a channel. What's that? What's the problem with making this roller go down the channel? You've done this before. You've tried to
twist.
roll. Yeah, it's going to twist, isn't it? And what's it going to twist because of? What are the factors that are going to cause this thing to, as it goes down, to want to twist instead of, you know, our goal is roll straight, but what's going to cause it to want to twist instead of roll straight?
The load?
Yes, perfect. One of the things that's going to happen is if you load this, let's see, what color do I have left? Let's load it. So if we load it mostly over here for some reason, and it's unloaded over here, you've changed the dimension of it, didn't you? This end over here is squished, and this is not squished. This is deflected, that's not deflected. What's it going to do? Roll. This end is going to roll at a different velocity than that one, just from loading. Okay?
You could do the same thing with heat.
Huh?
You could do the same thing with heat.
You could do the same thing with heat, so you better figure out how to do that. Although these bearings, that's a good point. Any idea what the efficiency of these bearings is? How much is going to heat of a ball bearing? It's like, it's very high, right? Not much of this isn't not typically a device that's getting heated up, because the efficiency is in the high 0.9s. You're not losing much energy out of here. So it'd be actually hard to get much heat into this thing unless it's really high speed, really under load. Then the heat would come from deforming. And as soon as where does the heat come from in something like this? The heat comes from the roundness. Let me get back to, the roundness. Come on. It starts out round, but then as soon as you put it on a flat surface and ask it to go down a flat surface and load it down, at some point right down in here, it's flat. And thus you have different velocities as it travels. Okay, so heat, what else? What else would cause this thing to skew in its travel?
If your load is off center, like, then it's going to want to try and twist it as opposed to move it directly forward.
You mean if the load is, for instance, over here more or over here more, that it's got certain moment load, same kind of thing. Yeah, loading is going to, any sort of non-perfect loading is going to deflect in more parts than others, right? Okay.
Yeah.
What else?
Is it also kind of similar to the previous bearings where it depends how straight that channel is?
That's the thing. That's exactly the thing, is how, what made this channel way back when you were making this channel, there was some machine tool that came down here, right? Some sort of machine tool that this is a machine tool spinning here. And it came down in that groove and it went back and forth and it made that groove in there. And you may have machined it, and then you may have polished it, you may have hardened it, you have to do, so we have this groove, but no matter what you do, it's only as good as the machine it was made on. And so that means it has tolerances and it's not perfect. So it's a bumpy road. It's a bumpy road for this roller bearing, way less than we can really imagine, but nevertheless, it's a bumpy road. And so every time this roller has to go up and over a bump, it has to travel further on one side. That, if we put a little bump in here that it has to go over on that side, then all of a sudden this part of the roller has to go further, but yet this one is only rotating a certain amount, and so it gets behind. And the trouble is, if you've ever done something like this where you run two things between rails, when you have a rail on each side and one side starts to get a little bit behind, it's the kind of thing where once it gets a little bit behind, there's no recovery for it. It doesn't magically catch up because the forces are such that it just wants to bind immediately. And so you have to keep it in this perfect region and keep it non-binding the whole way, because as soon as it does bind, it's bound, and it doesn't, trying to keep it going forward more only binds it more. So it's a non-recoverable bind if you ever do get one of these bound up in a channel. These tend to be called, the name for these they're called crossed roller bearings, is what they're generally called. And what you do is you don't just have one running down a channel, you actually tend to have two channels, and you have the bearings that are angled, and they still have to run down a channel, but they have to do some sort of preload. This is kind of hard to preload when there's only one. You really can't do it too well, because unlike a ball, which you can make run down a groove, you really can't make the sides of this hold it in, because all they'll do is cause binding. So what you have to do is have two sets of bearings, and they have to be at crosses. And it's a cross where I can't really draw it very good. So if you're really interested, go look it up. I'm more exposing you to it in class than I am asking you to remember it or use it in a design. But at some point, there are times when you need a lot more load carrying capacity out of a small size. And the only way to get that is to change from point contact with ball bearings to line contact and rollers. Okay. So most bearing manufacturers make both kinds. And this kind is, this is the $5 signs one, cross roller bearings, because they're so hard to manufacture. They carry a lot of load. That's kind of like the top of the line. There's maybe 0.5% of all bearings that are used in motion control might be a cross roller bearing. There's not that much use for it, but it's there. Okay, one last type that I would mention. Another type of bearing is the V-groove. This is what you're looking at here. There's one more type. And the main manufacturer of this is, it used to be called Bishop Wisecarver. They're actually down, they're bearing manufacturer down in the Bay Area of all places. And this is kind of a variation of that they actually have some sort of roller that has something like that. And then if you look at where it actually rolls in this, they actually have it rolling right here and right here is how they get this roller. I'm not sure exactly. They don't roll it on the point. They actually have some load carrying surface here and here. And the roller, this is actually, this, hold on. This part here is actually the rail. And then you would have the actual bearing is a little roller. And the roller has, the exact shape to it that you're after. Two of these rollers you always have to preload a bearing. These are fixed on center. This one and this one are fixed on center. This one and this one, you can't really see it, but they're on a little eccentric cam. So to preload this bearing and get rid of the slop, you would loosen this up, twist it a little bit, and then tighten it back down. So it's worth mentioning because, again, it is a fairly low friction. And one of the cool things is curved rails. This is more like what you would make a monorail or something. So this rail, they can take this part here, and if they do the interaction between these two bearings right, there's no reason that this rail can't curve between them. Right? So it can go up here. So on this, where we have the bearings, they'll actually be able to do some sort of curvature like this. And all of a sudden now you have curved motion instead of straight line motion. And sometimes you need that. And then you can, it's fairly easy to make this because they don't, it's a pretty easy adjustment to do right in here with the eccentric, whether it's straight or not. So it's kind of a cool little bearing to know about. And the other key thing about this is it's fairly, I don't know, let's call it debris free. Meaning if you put this into like a grain elevator and had sand or had wheat or rice or something dropping onto this whole bearing structure, the nature of these V-groove channels is that nothing sticks in them. This is a little ball, and so if you look at it, there's I wish I should go get some rice and just dump it on here, but everything would fall right through. There's no surfaces to collect dust, and there's no lubrication. And you don't need a lot of lubrication where you don't have a lot of friction. You don't need a lot of lubrication. You only need lubrication where you've got a lot of friction. So kind of a neat bearing.